In this section, we're going to explore functions and their graphs just a little bit, deeper than what we've talked about. So let's talk about graphs of equations, just some things that you're going to see in this section. We're going to be able to sketch graphs of equations. We're going to identify x and y intercepts. We're going to talk about some symmetry with respect to the x-axis, y-axis, and origin. And then we're going to be able to write equations and sketch graphs of circles. And then we're going to look at a real-world example. So let's talk about the graph of an equation. When we talk about graphs of equations, we're going to talk about relationships really between x and y. When we talk about equations in this sense, we're talking about equations in two variables. Now, if you go on to other courses, you can talk about three variables and what that would look like. But we're really going to focus on two variables in this course. So for instance, what if we have this equation y equals 7 minus 3x? And that's the equation that's written in terms of two variables, x's and y's. How do we know if we have a point that's on that graph? Well, any point that's on that graph would have to make a true statement. So, and those points that are on that graph are called solution points. And that happens when we plug that x and y value in and we get a true statement. So for instance, suppose we have the point 1, 4. That's going to be a solution of y equals 7 minus 3x. Because if we have, and I'm going to write it down here, we have an x and a y value. And if we were to substitute everything in, we're asking, do we get a true statement? Is 4 the same thing as 7 minus 3 times 1? Well, we know that it is. So because we get a true statement, then we say 1, 4 is a solution of that equation. Let's look at another example. Is 2, 3 a solution of the equation? Now I'm going to use the same equation. So to figure out whether or not it's a solution, we're just going to substitute in everything we know. We know that our y value is going to be 3. So we're asking, is 3 equal to 7 minus 3 times x, and our x is 2. So is 3 equal to 7 minus 6? And we know that no, that's not going to be equal to. So we would say no, 2, 3 is not a solution. So what it means to be a solution is that this point is actually going to lie on top of that graph. So I want to go back to GeoGebra. Let me delete a few things here. So we're going to type our equation in, y equals 7 minus 3x. So there's our graph. And that first point we looked at was the point 1, 4. So let me show you graphically why that was a solution. So do you see our line over here, that gray line, and then you see that dot right here? So you see how that dot lies on that line? Since that a value lies on top of that line, then we say that that's going to be a solution. But then when we typed in 2, 3, look at what's going to happen here. 2, 3, our B point, is not on top of that line. And that's why that 0.23 was not a solution, because it's not satisfying the requirements. And the requirement is you have to lay on top of that line. So we can see it graphically and we can see it algebraically. So now let's talk about graphing a little bit more. How do we go about graphing an equation? Well, one method of graphing is by plotting a whole bunch of points. So if it's possible, we want to take that equation and we want to isolate one of the variables. And all that means is we want to get x or y by itself. And that just makes it easy to type in a whole bunch or plug in a whole bunch of values and get out the other values, which makes it easy to find ordered pairs. And we can organize all that information into a table, and then we can take those points, put them on the rectangular coordinate system, and draw a picture of what we have. Now, it's important to use a variety of numbers. Usually you want to use negatives, zeros, positives when you try to construct a graph. As we progress through this course, you'll have the idea of some basic graphs and the forms of those basic graphs. So you'll have an idea of what are good numbers to plug into equations to generate a good sketch of what the graph would look like. So let's look at this. We have y equals negative 3x plus 7. We want to sketch a picture of this graph. Now, if you think back to an algebra class that you may have taken in high school, you know this guy is the equation of a line. So let's pick some x and y points. Now, I've gotten y by itself here. So we've got y isolated, and that just makes it easy to plug a whole bunch of x values in and generate a whole bunch of y values pretty quickly. That's the whole reason for that isolation step. So we're going to plug in some x's and y's, and then we're going to think about these as ordered pairs. So I'm going to plug in negative 2, negative 1, 0, 1, and 2. If we were to substitute in a negative 2, we have y equals negative 3 times negative 2 plus 7. So that's going to be 6 plus 7, which is 13. So my ordered pair is negative 2, 13. If we substitute in negative 1, I'm changing this guy to a negative 1. We're going to have 3 plus 7, which is 10. So my point is negative 110. If we plug in 0, we're going to get 7. If we substitute in 1, we're going to get 4. And then if we substitute in 2, negative 6 plus 7 is 1. So there's my ordered pairs. I do want you to notice something about the x's and y's here. We chose the x values, and I just chose, just started with negative 2 randomly, which is fine when you're trying to sketch. But I increased by 1, so I have that constant increasing going on. That's important because then we can kind of analyze what's going on with y. And notice y is constantly decreasing. So that's telling us a little bit about what's called the slope of this graph. And we can see that if x has a constant increase or decrease and y has a constant increase or decrease, then we usually we actually will have a linear function, which we'll talk more about later. So for now, let's talk about graphing. So if we were just to plot all of these points, so here's negative 2, 5, 6, 7, 8, 10. So here's negative 2, 13, negative 1, 10, 0, 7, 1, 4, and 2, 1. So now we have all of these points, and we could connect the dots. So we could keep going. So there's our sketch of this graph. So now that we've talked about how to sketch, let's talk about how to find intercepts. Intercepts are places where the graph is going to cross either the x-axis or the y-axis. So let's look at a few pictures. Now, it's possible that we may not have any x-intercepts or y-intercepts. We could have one intercept. Maybe we have just a y-intercept or just an x-intercept. Or we could have several going on. So let's look at that first picture. That first picture is what's called a quadratic function. Okay, notice that it's not crossing that x-axis at all, but it does cross the y-axis at one point. So we would say this does have a y-intercept, but no x-intercept. If we look at that second picture, this is what's called a cubic function. Here's my y and my x-axis. Do you see how that graph's crossing the x-axis 3 times? That means we have 3 x-intercepts. Do you see how that graph crosses the y-axis 1 time? That means we have 1 y-intercept. Now this one's interesting because it's going through that origin. And the origin, because the graph goes through the origin, that point 0, 0 actually it classifies as an x-intercept and a y-intercept. That is the only point that could be both x and y-intercepts. If we look at the next picture, that graph crosses the y-axis 2 times. So we have 2 y-intercepts. And it crosses the x-axis 1 time. So we have 1 x-intercept. And then that last graph, we have a circle. And notice that circle is not crossing the y-axis or the x-axis. It actually lives completely in quadrant 2. So we would say there are no intercepts for that particular figure. When we talk about how to write x-intercepts are always going to cross the x-axis, which means it's going to have an x-coordinate, but the y-coordinate is always going to be 0. So the ordered pair for an x-intercept could be written as an x-coordinate, and we could just generically call it A, and the y-coordinate 0. A y-intercept has to live on the y-axis, so notice that x-coordinate is always going to have to be 0, but that y-coordinate is going to have some value, and we could call that value generically B. So all y-intercepts can be written as an ordered pair 0B. So now we've kind of built up to the question, well, how do you find x-intercepts algebraically? If you want to find x-intercepts algebraically, we know an x-intercept has to live on the x-axis, which means that y-coordinate is going to have to be 0 because we're not moving up or down from the x-axis. So if we let y be 0 and substitute that into the equation and then solve that equation for x, then we will get the x-intercept. And x-intercepts, like we said before, can be written in terms of whatever the x-coordinate is, but the y-coordinate is always going to be 0. Likewise, if we want to find a y-intercept, now we're trying to find where it's crossing this y-axis. Well, that x-coordinate is going to be 0 because we're not moving left or right. So we're going to let x be 0. And now that we have x is 0, we can substitute that into the equation, and then we can solve that equation for y. And then our intercept can be written as 0 because that's what we plugged in for x. And then whatever we get out for y, which we can call b. Let's look at an example. Let's say we want to find x and y intercepts of the function y equals x cubed minus 4x. To find the x-intercept, we are going to let y be equal to 0. So if we let y be 0, we have this guy. And we want to solve this. So we know we could do factoring. We could pull out an x, and that's going to leave us with x squared minus 4. And then we also know this is a difference of squares, which factors into x minus 2 times x plus 2. So then we can set each factor equal to 0. So we have x equals 0, x minus 2 is equal to 0, and x plus 2 is equal to 0. So we have an x-intercept at 0, we have 1 at 2, and we have 1 at negative 2. If we wanted to write these as ordered pairs or points, my first one is going to be at 0, 0. My second one is going to be at 2, x-intercept at 2. We plugged in y for 0, so that y coordinate 0. And then my third one, I had a negative 2 that came out for x. And I have 0 for my y because that's what we plugged in. We know it has to live on that x-axis and that y coordinate's always 0. To find a y-intercept, we are going to let x be equal to 0. So if I substitute in 0 for x, I'm going to get 0 in this case. So my point, I only have one here, is the point 0, 0. So those are my x and my y intercepts for this problem. So now let's talk about symmetry. Graphs of equations can have symmetry with respect to one of the coordinate axes or with respect to the origin. So when we talk about symmetry, we could have symmetry with respect to x. And what that means is that if we were to take this figure and we were to fold it along the x-axis, the top and the bottom halves would completely match up. So you could take this, draw it out on a piece of paper, and you would see how the top and the bottom halves would match up. That's what it means to have symmetry with respect to the x-axis. If we have symmetry with respect to the y-axis, here's my y-axis in this figure. If I were to fold this graph along that y-axis, do you see how the left and the right-hand sides would match up perfectly? That's what it means to be symmetric with respect to y. Now, if we want to be symmetric with respect to the origin, I like to describe this as a two-step process. You have to be able to fold this graph along x and y, and if those pieces match up, then you're symmetric with respect to the origin. So let's look at this example. So here's our graph. So if I were to take this piece and I were to fold it along the x, do you see how it would show up down here? And then if I were to take that and fold it along the y-axis now, do you see how it would match up with what's there, with that black piece? Symmetry with respect to the origin will always have those two folds. Always think about it in terms of folds. Now, let's talk a little bit more about what's going on with those ordered pairs. And I'm going to go back to this figure where we were symmetric about the x-axis. So we know it's symmetric about the x-axis because if we fold it, the top and the bottom halves match up. Let me change my color. So you can see how the top and the bottom halves match up. So that means that this point, if it has to match up, it has to match up down here. Well, the x value, how far it is from the origin is going to stay the same. What's going to change is that y value. So it's going to go from a positive y to a negative y. Let's put numbers with this so you can see it a little bit better. So we have something that looks like that. And we have this point, maybe it's 2, 3 here. To be symmetric with respect to the x-axis, we would fold along the x-axis. This would have to lay down here at the point 2, negative 3. Now that has to happen not only for that point, but for every single point along that graph. That's why we use generic points, x, y, to describe that type of symmetry. The same concepts can be applied to symmetry about the y-axis and about the origin. If we talk about symmetry about the y-axis, I'm talking about folding along the y-axis and the left and right-hand sides matching up. So if we pick a generic point over here, xy, and we were to fold it along here, do you see how the height, that y value would be the same? But what changes is that x value. Instead of moving, let's say this is the 0.31. Instead of moving 3 places to the right, when I fold it, I now would move 3 places to the left. And then if we have origin symmetry, think about what's going on in this picture. We have this point, generic point xy. We started in the first quadrant. We need to do 2 folds so that we end up in the third quadrant. So it's going to change both the signs of the x's and the y values. And that actually gives us an algebraic type of test to be able to describe the symmetry. If we're symmetric with respect to the x-axis, then if we were to substitute in x negative y, then that point also has to be on the graph. So let me give you an example. Let's say we had the graph x is equal to y squared. That graph, if we go to Desmos, is a quadratic that's sideways. So you can see our graph. Now you can see there's definitely symmetry with respect to the x-axis here. So now let's show it algebraically. Let's plug in the point x negative y. If it's symmetric with respect to the x-axis, then we should get the same equation out. And if we substitute in negative y squared, it's negative y times negative y, which is a positive y squared. So we do get the same equation out. And all that's saying is that any point that's up here on this graph has to also live down here on this graph. You can see how it's changing those y values. If we talk about symmetry with respect to the x-axis, let's look at y equals x squared minus 4. So let's look at what would happen. I'm going to delete and type in my new equation. There's my graph. So we can see there's definitely symmetry with respect to the y-axis. If we were to fold this along the y-axis, the left and right hand sides would match up. So what this is saying is that if I pick an xy ordered pair, then negative xy is also going to be on the graph. So we could just make that substitution in here to show it algebraically. We would substitute in negative x and y. And you see how we're going to get the same thing as what we started with. I think symmetry with respect to the origin is a little bit tougher to see. We're going to look at y equals x cubed. There it is. So we see we have symmetry with respect to the origin. We could think about those folds again along the x and then along the y, and how the piece in the first quadrant matches up with the piece in the third quadrant. So what this is saying is that if I pick a generic point on the graph, x, y, then negative x, negative y also has to be on the graph. So if we were to substitute in negative x, negative y, then you're going to see those ordered pairs come out. Negative x to the third is negative x times negative x times a negative x, which is a negative x to the third. So every ordered pair would look like that. So let's look at this guy. We have y equals x squared minus 2. If we were to graph this function, we'll see the symmetry we have. Oops. So there's our graph. What type of symmetry do you think we have here? And that is correct. We do have symmetry with respect to the y-axis. So with respect to, I'm going to abbreviate the y-axis. So once again, we can talk about our algebraic test. The graph of an equation is symmetric with respect to x-axis. When replacing y with negative y yields an equivalent equation. We saw that over here. We substituted in a negative y. We got the same thing that we got before. The graph of an equation is symmetric with respect to the y-axis. When replacing x with a negative x yields an equivalent equation. We saw that here. We substituted in a negative x, and we ended up with the same equation we started with. And then in 3, if we want to be symmetric with respect to the origin, then if we replace x with a negative x and a y with a negative y, notice you got to do both, then we're going to get an equivalent equation. And that's exactly what happened in that last example here. We substituted in negative x, negative y. So we have negative y is equal to negative x cubed. And if we were to divide everything by negative 1, we get the same thing as what we started with. So going back to that previous example, graphically, we saw it was symmetric with respect to y. We want to prove that. We're going to substitute in a negative x. And then if we simplify that, negative x quantity squared is an x. That is the same thing that we started with. So there's your proof that that is symmetric with respect to the y-axis. Now suppose we want to look at this example. We want to sketch a graph of this equation. Now notice this is an absolute value equation, and usually we see absolute values with a V-like shape. So that's what we're going to expect to come out of this. So let's pick some points. So I'm going to create my table again. And I'm just going to pick some values. Negative 2, negative 1, 0, and 1 and 2. If we plug in negative 2, we would have y equals negative 2 minus 1 absolute value. So that's absolute value of negative 3, which is 3. So our point is negative 2, 3. If we substitute in negative 1 minus 1 is the absolute value of negative 2, which is 2. If we plug in 0, and then if we substitute in 1, oops. And then finally, if we substitute in 2, so we can plot these points. And keep in mind, these are all rough sketches. We could get better sketches if we had like a piece of graphing paper to get that. So here's negative 2, 3, negative 1, 2, 0, 1, and then 1, 0, and then 2, 1. And you can see that V shape coming out there. So there's our graph. Now, think about symmetry. Does this graph have any type of symmetry? Well, if we were to fold it along the x-axis, there's nothing down here to give us symmetry. So it is definitely not symmetric with respect to the x-axis. Is it symmetric with respect to the y-axis? The answer is no, it's not symmetric with respect to the y-axis. If we were to fold it along this y-axis, the left and the right-hand sides will not match up. Is it symmetric with respect to the origin? And the answer is no, it is not symmetric with respect to the origin. If we were to fold this along the x and then the y, there's nothing in that third quadrant to line up with what's in that first quadrant. So this guy actually has no symmetry. And then now we need to talk about circles. When we talk about a circle, we need to talk about what it means to have a diameter and a radius and a center. The center of the circle is really the middle. The diameter of the circle is the distance all the way across. It has to go through, that segment has to go through the center. Now, half of that is called the radius. Half of that distance is called the radius. So we could talk about the radius here. So if we knew the center and we knew a point on the graph, so let me erase this. So we know the center is here at the point HK, and we knew another point on the graph here. Then to find the radius, we could use the distance formula. Remember, distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. So if we're looking for that radius, then we could apply that distance formula to get that just by using that point xy in that center HK. So then if we were to take that formula by using those 2 points and square both sides, we will get the standard form of an equation of a circle. Squaring a square root cancels everything out, so we're going to be left, with that x minus h squared plus y minus k squared, and then if I square r, I get r squared. Now, if this circle happens to have a center of 0, 0, then we would plug a 0 in for h and a 0 in for k, and that would leave us with an x squared plus y squared is equal to r squared. So let's look at an example of circles. The point 3, 4 lies on the circle whose center is at negative 1, 2. And we have a picture that shows that. We want to write the standard form of the equation of the circle. So we know the center, HK, is at negative 1, 2. We need to find the radius. So how far is it from negative 1, 2 to 3, 4? That's what we need to ask. So that's where we can use our distance formula. So we're going to have 3 minus negative 1 squared plus 4 minus 2 squared. So this is going to be 4 squared plus 2 squared. So that's 16 plus 4, which is the square root of 20. So now let's take all of this information, our HK and our R, and let's substitute it into our formula. So we have x minus negative 1, that's our h, squared, plus y minus k, which is our 2, there's our hk. And that's going to be equal to the square root of 20 squared. So we have x plus 1 squared plus y minus 2 squared is equal to 20. So there's our standard form of the equation of a circle. So I want to look at 2 other examples. of circles. Let's say we want to find the center and the radius of the circle given the standard equation x minus 1 quantity squared plus y plus 3 squared is equal to 9. So let's compare this to what our standard form looks like. Remember, standard form is x minus h squared plus y minus k squared is equal to r squared. So we really need to think about how can I rewrite this to fit that form. Notice I've got to have a minus h here, and we'll have to have a minus k here. So it's pretty easy to see what my h is, but I have to think about my rewrite for this term. I can write that as y minus negative 3. That's the same thing as a positive 3 here. And that makes it easy to identify my k, which is the y coordinate for the center. And I can think about that 9 as 3 squared. So then my center is at the point hk, which is 1. Remember, h is the number after the negative. And k, which is negative 3, is the number after that minus sign here. And then my radius is 3. Let's look at another one. Suppose we want to write the standard form of the equation of a circle with the center at negative 4, 5 that has a radius of 2. Standard form looks like this. And all we have to do is substitute in the information we have. So we have x minus negative 2 squared. That's our h. Our k is 5. Our radius is 2. So we have x plus 2 squared plus y minus 5 squared is equal to 4. There's our circle. So let's look at an application, and we're going to use the TI graphing calculator to demonstrate what's going on here. So in this example, the median recommended weight y in pounds for men of medium frame who are 25 to 59 years old can be approximated by the mathematical model y equals 0.073x squared minus 6.99x plus 289.0, where x is between 62 and 76 inclusive. And x is going to be the man's height in inches. We want to construct a table of values that shows the median recommended weights for men with heights of 62, 64, 66, and so on. And then we're going to use the table of values to sketch a graph of the model. And then we're going to use the graph to estimate graphically the median recommended weight for a man whose height is 71 inches. And we're going to use the model to confirm all of that. So I'm going to go to my graphing calculator. Here she is. And then I'm going to go to y equals, and I'm going to type this equation in. So it's going to be 0.073 x squared minus 6.99x plus 289.0, or just 289. And I'm going to hit graph. Now, the standard window is a 10 by 10 window, meaning that it's going to go 10 units to the left and to the right of the x of the origin, and the 10 units up and down from the origin. Now, that's not going to help me see this graph, and as you can see, it's not on there at all. But if I go to zoom, and sometimes zoom fit is a good place to start, then it will kind of readjust the scale so we can see what's going on. Now, if you think back to an algebra class, this should look like a quadratic, but our window needs to be altered a little bit. So I'm going to change this x-min and x-max. So notice that it says that x has to be between 62 and 76. So let's go from 60 to 80 here. X scale, I'm going to go up by 2s. And then my Y min and Y max, let's leave that just to see what this graph is going to look like. Finding the right window sometimes really is just playing with that graph. So now I'm going to change this a little bit. Let's go from 0 to, let's try 60, see if that does us. Let's see how that looks. So if we read back through the problem, Y is weight. Let's try 250, see what that does. There's my graph. I'm going to change my window just a little bit more. Let's go down to 40. Even though X is between 62 and 76, I want to see a little bit more of this graph. So you can see more of the curvature here. It's a quadratic. We can see that it's opening up. They're asking us to construct a table of values. So there's a nice, easy way to get all those to get that table of values in the calculator. I like to set my table set. If I hit second and window, I like to set my independent variable to ask. And what that will let me do is type in a bunch of X values, and then we'll get out a bunch of Y values. So I'm going to hit second and then graph, and that takes me to my table. So notice it says X and then it says Y1. This is going to allow me to type in these numbers like 62. And then it's going to tell me what the weights are. So 62, I would get 136. I can type in 64, 66, 68, 70, 72, 74. Oops. That should be a 72. And then I can type in 76. I'm just going to have to type over the 74. So those are my different heights. So you can see all these Y values. Now we can take them and we can organize them in a chart. So the height is 62. The weight is 136.2. The height is 64. The weight is 140.65. The height is 66. The weight is 145.65, and so on. So if we were to organize all of that information into a chart, going back here now, our chart would look like this. So those are the heights, and these weights are found just by plugging those values in. Now, they're asking us to estimate what the value would be at 71. So we could take all this, we could plot it on a Cartesian plane, we could do it in Desmos, we could do it in GeoGebra. We've got it on the calculator already, so I'm just going to pull my calculator back up. So I need to find 71. I'm going to change my window a little bit here. And let's just put this at 70. So I can see 71 pretty easily. And I'm just going to go up by ones now. So here's 71. We need that height. So we can have the calculator give us that height by going to second calc, and we want the value. So we're going to hit enter, and this is going to give us the exact value at 71. And that exact value is 160.7. Now, if we wanted an estimated value, which is actually what they asked us for first, the estimated value can be found by hitting this trace button. So you see when you hit trace, that blinker pops up, and it tells us where we're at. We're actually pretty close to that 71 now. So if I were to scoot over just a little bit, I'm a little bit closer to 71 than I was. So that estimated height is 160.9. So here's our picture. Like I said, we could draw it by hand. We can estimate 71 inches. And when we did this on the TI calculator, we got 160.9 just by using that trace feature. So then they asked us in the next part to confirm it just by plugging that number in. So if we plug that 71 in for those X values, then we get 160.7, which is really close to what we got when we hit trace. And like I said, we can find that value easily on the calculator by hitting second and trace. That takes us to our calculate menu and using that value feature and typing in 71. And that's exactly what the calculator is doing. It's taking that 71, plugging it into that equation, and that's where the 160.7 is coming from. So it's a fast way to do that instead of having to do computations by hand. We will use the calculator throughout this course, and I'll show you different things you can do on it. So good times coming up ahead.